So this is an intro to Rust for Substrate developers. Please give Maciej a warm round of applause.
Cool. So I have like 45 minutes to teach you Rust, which is impossible. Who has done any Rust at all? Okay, there's some hands. Keep your hands up. Who has done Rust and hates the borrow checker? Oh, that's pretty good. Okay, fine. So first of all, who is this for, right? If you're coming from like C and C++, or you're coming from like the other end of the spectrum, you're coming from like JavaScript, Python, whatever, you will be good. If you're a beginner, you're good. Or completely new, you're also good. If you're kind of intermediate, you might still pick something up. Like there are things here that I didn't know like a year into my coding in Rust. So hopefully there's like something useful for everyone. Yeah, kind of around. So mostly if you're working with Substrate, this is for you. There's also Ink, which is the kind of embedded domain-specific language for my context in Rust, which also compiles to assembly. So that's kind of also useful there if you want to do that. And yeah, and mostly like I cannot teach you Rust in 45 minutes because that's impossible. What I can do is at least like show you all the things and shine you some light, and maybe you can find the unknown, so you'll at least like know what you don't know that you can learn. It's kind of helpful. So what are we going to cover here? It's pretty awesome. So Rust philosophy, the first thing, which is like just what are the principles and some broader review of the code, and that kind of by example shows why this is kind of useful. Very basic, so primitives like numbers, stuff like that, pretty basic. Error handling, implementing methods on stuff. Trade system, which is super cool, and should time permit lifetimes. It's like I don't know how long this is going to take necessarily. I have pauses for questions in the middle of the talk. So basically, after each section, there will be a short time for questions, hopefully, and depending on that, whether there are questions or not questions, or whether people want to like speed things up, I can like go slower, faster. We'll see. So yeah, what I'm not going to cover: closures. They're kind of like same as JavaScript and Python. Does have Python have closures? I don't know. But definitely JavaScript and Ruby, very similar. Nothing crazy. You can figure it out. Multi-threading, mutexes, message sending between threads, very useful. Not going to cover it. Unsafe Rust, which is like the escape hatch that we have. Like, Rust is very safe as a language, but there are some things you kind of want to do occasionally that you can't really express in the safe Rust, and there's the unsafe superset of the language that I'm not going to talk about. It exists. Usually you don't really you have to have really good reasons to do it. Don't do it. Macros are actually used a lot in Substrate, but they're impossible to talk about, A, in short time, and B, they kind of break a lot of like syntax assumptions. So you kind of have to like, for Substrate specifically, you kind of have to look at the macros that you're using and find recommendations for them, because there is no generic way to approach macros. Unfortunately, like they can do anything. They're magic. How types are represented in memory, and like a lot of other things. There's like a whole lot of Rust stuff. So yeah. So with that, what's Rust about, right? What's the kind of philosophy of Rust? And when you think about programming languages, typically or historically, you have like the spectrum where on one side you have C and C++, which are high-performance languages. You do like operating systems in, and you do cryptography in for some reason, which is a horrible idea because they're horribly unsafe. Like you can shoot yourself in the foot in C++, times over, where in language like JavaScript, like you can shoot yourself in the foot in JavaScript, obviously, but you cannot like do segfaults in JavaScript, right? The memory safety is guaranteed for you by the garbage collector. Same in Java, same in Python. So there's always like this tension between, or there used to be this tension between performance and safety. And Rust is basically the language that tries to address it by going, stepping outside of the spectrum. It's like, okay, we will give you the performance and we will give you the safety at the same time, like with no compromise. There's a price to pay for that, and the price to pay for that is the language is a bit more complex. And actually, it's more like this. It actually tries to give you more safety than even like the considered safe languages. Like it tries to go a step further than that, which is why it actually makes perfect sense for you to use Rust for blockchains, because you want your code to be correct on the, like you don't want horrible things happening on the blockchain. There's kind of cool cartoon, which is like there's a programming people page that kind of like has drawings of like the programming languages of people, and like Rust is this character of like full suit of armor with 2 shields, like I'll be designated driver tonight, and like we know, well, don't talk while eating, you can choke. That's kind of like the annoying borrow tracker compiler, whatever stuff, and it's kind of true. So we have this motto of like, okay, there's safe, concurrent, fast, big 3. Like you get all of the package, right? But some cost. There's another picture that's cool. As David Barron from Mozilla in the San Francisco office, and he has like this paper on the wall. I don't know if you can read it. It says, "Must be this tall to write multi-threaded code," which is like also like one thing that Rust excels at is writing safe multi-threaded code, where multi-threaded code is like this thing that wizards do in their towers and normal mortals like never touch. In Rust, you can write, even if you're a novice, you can write multi-threaded code, and you are sure that you don't have that races, and you don't like share mutable memory around, like things like that. So that's pretty cool. So Rust. Rust doesn't have runtime overhead and doesn't have a garbage collector. It does have runtime, I was told, but it doesn't have runtime overhead. So which means like when you're executing your code, the only thing that is being executed is your code. There is no extra process attached to your code. And it also has CFFI, so foreign function invocation kind of ABI, which means Rust is very nice in terms of like you can make your Rust pretend that it's C and then like link it to C, and the other way around you can kind of embed Rust in anything that you can embed C in. So that's kind of cool. It has zero cost abstractions like C++, which I'll demonstrate later. It has the ownership model, which is a thing that helps it manage memory, and that's basically where the memory guarantees are coming from. And it will hurt your feelings because it's actually opinionated. So there's things you don't do in Rust, like you don't do inheritance, and you do composition, and it's things. But it will also empower you. So the code you will run, once you get like familiar with the language, you will feel more comfortable about the code you're deploying, because the safety guarantees you get from the language, you will like feel more confident, and will empower you to write more complex code without feeling like I don't know if this is going to send some nukes somewhere or whatever. So this is like a piece of code I wrote that kind of demonstrates what it can do. So this is pretty simple. There's 2 functions, so don't be afraid. So there's a function, bunch of numbers, returns a vector of U32, which is a 32-bit integer. And then we try to like print out the last number. We call this function, and we print out the last number, depending on what it is from this function. So we create a vector, which is kind of like growable array. And then we loop, we do a for loop from 0 to, for 10 iterations, to 9, technically. And then we push onto the vector, and then we return it. Like Rust has implicit returns. If you don't have a semicolon at the end, that is a return. So there is also a return expression, technically. So you can also do return something and semicolon, that also works. So the cool thing about this is, if you know Rust, you already know, because Rust is a low-level language, if you know how Rust works, you actually can figure out some things on like low level. So you actually know that, okay, creating a new vector doesn't really do anything, but when I'm pushing it into a new vector that hasn't been initialized, then I'm doing an allocation, and then I will probably do reallocations when the vector grows. Then the last line will move the vector, which is like a semantic thing in the language. Returning a value that is owned means I'm moving something away. And then when I'm calling the function, I obtain the ownership of the return value if the value is owned, if it's a value type. And then I do some stuff, so I match on the last value. If it's sum of 0, so if it's 0, then it's 0. If it's a number, then it's print me the number, and if there's none, there are no numbers. And then at the end, because I have a value in the scope of the function, I have value type that is owned in the value in the body of the function. At the end of the function, the compiler will insert a drop instruction for this type, which in this case, because vector is a heap allocated structure, it will deallocate the thing. So it's kind of useful. But we are Rust, so we can do some things better if you can analyze it. So we can initialize the vector with capacity of 10, because we are iterating over 10 items. And you can kind of do the same analysis here. Okay, now by pushing to the vector, it will never actually allocate because I have enough capacity. Capacity is different from length in the sense that you can have a vector that has, you always have to have more capacity or more or equal capacity to length. But you can have a capacity of 10 and length of 0, which is what this will be at the beginning. So this kind of works the same way. And you can also do something even more clever, which is this kind of little snippet. So you create you do this 0 to .10, which is a range. And the range is also an iterator. And you can collect iterators into things. So you can collect an iterator into a vector, which is kind of useful. And this kind of demonstrates the kind of zero-cost abstraction expressiveness of Rust, right? And it's kind of the same way. It's allocation plus move, all in a single step. So I have this very, very short bit of code that compiles to very, very efficient assembly, right? It's very nice. It's people from high-level languages really like this because it's kind of Haskell-y and magical and whatever, but it compiles to really, really good assembly code that just runs very fast. Actually, in a lot of cases, this will run faster than a lot of handwritten code because the compiler can make some assumptions about bounds checking and things. So that's cool. So first intermission. Are there any questions about this? Okay.
When you call collect, how did it know to collect into a vector? Is there type inference or something?
There is a type inference, and there's a trait that's implemented for the range or for different collection types that will try to figure out. It's a thing. Okay. Sure.
When you're talking about vector, is it just a global list?
Yes, it's basically a global list of a single type.
Okay, and the first pattern match last number is 0.
Yeah.
Can you please elaborate on syntax here? You just.
I will get to match expressions. That will be easier later. But yeah, I'll explain how this works. Okay. Okay, primitives. Primitives is fun. So there's a Boolean, obviously. There's a char, which is the Unicode code point. That's 4 bytes, whatever, used for some things. There are unsigned integers, and there's multiple of them. They all follow the same pattern in the naming. So there's U8, which is the smallest one, which is a byte, 8 bits. And then there's the largest one recently added, which is U128, so 128 bits. And there is this kind of special magical one, which is usize. And usize is a pointer-sized integer. And pointer-size basically means it's whatever architecture you're compiling to, that's the size. So if you're compiling to 32-bit CPUs, then it's 32 bits. If it's compiling to 64-bit CPUs, then 64 bits. And this is, well, I'll explain later, but this is there are reasons to use it. There are signed versions of Dust, so the same, but there's I for integer or U for unsigned integer. And then we have floating point numbers, 32, and so single precision and double precision floats. Somehow Rust has I think more sane nomenclature here, they kind of look more arcane, but in C you have I don't know, char and long and integer or int and whatever, and it's kind of you have to know which one is which size, and here you actually have the size directly in the type name. So choosing the Rust, the right number type. So if you want a float, well, you probably want to use 64-bit floats, unless you're doing games and you want high performance, and you're okay with 32-bit floats. If you want a length or you want to index into an array, then you use usize. And here, usize is actually very useful because you want to use the integer of your architecture to map into your memory. That's usually how it works. So that's kind of a good abstraction to do that. If you need negative integers, then you use any I type that's the smallest possible that you can use. Or I don't know, there are some heuristics you can use. I usually use 64 bits for most stuff. Same if you don't need negative numbers, which a lot of times you don't, then you use unsigned integers. Bytes are always U8, which I tend to work out of bytes. And the I size rarely used, like you mostly use it with like unsafe Rust with pointer arithmetic, so it exists, you can kind of know about it. You can use it if you want, but nah. Achtung, blockchain Achtung. Floats in Substrate are forbidden. We don't use floats, we don't like floats, because floats are not deterministic across platforms. So if you want to build a blockchain and you want to deploy on any hardware, floats are a very bad idea, because they can introduce like consensus issues, basically. So don't use floats. Okay, arrays. Simple value types. Arrays are very simple, so it's basically kind of like a vector, but they're not growable, so they're fixed size. You define the size on this like notation, so there is a type and there is how many of the type there are. There are tuples, which are similar, so there are a list of things, but the things can be different, so you can have a list of here, like a byte, a boolean, and a float. And you index them by a dot number, basically. And there is also the void tuple, which is the void type in C. It's basically an empty type. So, which is also the default type that is being returned by functions. So like if you will see an error that returning type X but expected empty braces, then you probably missed a semicolon. Or if expected type empty braces but got X, then you probably need to add an a semicolon at the end. That's kind of useful to know. And then we have slices, which are actually super cool, which are similar to arrays, but they are unsized, which in Rust speaking means that the size of the type is not known to the compiler at the compile time, but it's included in the will be in memory tracked on runtime. And you write it as similar to arrays, but you skip the size. In practice, you almost always you add ampersand. Because they are unsized, so you can't put it on a stack. There's compiler doesn't know how this would even possibly work. So you always have a reference, and the reference will then include the length of the slice. There's a sister or brother, I don't know, type to the slice, which is the string slice, which is basically a wrapper around a slice of bytes, but guarantees that it's Unicode formatted and you can print it and some cool stuff with it. So some code. So here I'm creating an array of bytes, of 5 bytes. I initialize it with zeros. And then I set the byte at index 1 to 1, byte at index 2 to 2. And then I do something magical. I can convert the array to a slice. So I index into the array using, again, the range operator. And this gives me a slice of, in this case, the first 3 elements. And then I print it with this crazy debug print. And it gives me 0, 1, 2. And that's my slice that I sliced out of the array. So you can slice arrays, you can slice vectors, you can slice a lot of things. You can slice slices. Tends to be very useful. And slices are 0 copy, so just create a new pointer and length kind of thing on the stack, and the data lives somewhere else. You don't care about it. So we have typing inference. That was a question. So you can create variables like this. Actually, the first one is missing. So we add let some variable name column type equals value. You can do that. You don't have to do that most of the time. You can just write stuff, and then Rust will figure out what the type of the thing is with some caveats. If you're doing numbers, if you do an integer, so there's no point something, then Rust will default to I32 unless there is some inference somewhere else. And if you want something else, then you can also do this cheat at the end. You add the type, and it's kind of type of the same, part of the same token, kind of of the number literal. So yeah, there's the string slice literal. There's a byte array reference literal kind of. There's the single byte literal, which only works for ASCII, kind of useful sometimes, and the char literal. Okay, and then finally, getting to the actually good parts, we have structs, which are kind of very similar to C structs. And structs are basically a collection of different types that have a common name and then can be referenced as types around your code base. You have zero-size structs, which is just a name that you have a type. which are not very useful if you're a beginner. They can be kind of useful in like later when you use generics. By themselves, they are kind of useless. There are tuple-like struct, which is useful if you just don't care about names. You just want to like do the 0.1, or you can just give them field names. They're when they're compiled, the tuple-likes and the field, the struct with a field names, they are kind of identical because they just hold the values, and it's just like for your information when you're writing the code. But yeah, that's it. That's kind of what the structs are. So here I'm. Here we go. Yeah. So here I have this example of the struct buzz, which has an ID, which is a usize, and there is a name, which is a string, which is a thing. And then you kind of create an instance of a struct this way. So you basically do the name of the struct, and you put the field names again, if you have field names, and then you just give them values, right? So I put 42, and then I put this. I create a string, owned string from a string literal or a string size literal, and then I can print some field names. So I can access the field names using the normal dot and the field name. Pretty straightforward. Nothing crazy. So this is kind of like the primitive object that you would use, except we don't call them objects. And then we have enums, which are similar to structs. If you're coming from C, then those are tagged unions. I don't know if that tells anyone anything. So yeah, enums have multiple variants, which can be different shapes, different sizes, and can have different fields. And there's a tag attached to it. So you always have to tell, or you have to know, or the compiler has to know which variant you're working with. On the stack, they are, if you care about stack sizes, it's the size of the largest variant plus the tag. So that's kind of maybe a high or low level, I guess. And the values in the enum are not accessed by the dot. You can't really do that. Like you could do that with unions. So we do pattern matching, which was the question earlier before. So let's say you can do simple enums that are just like lists of names, and they are basically simple enums, like I don't know, in TypeScript you would have it, or in Java, which is just like basically like a safe abstraction over like some enumeration. What you can do, and that's what mostly you use enums for in Rust, to represent like different a type that can have different shapes. So here I have an enum called number, and this number can be either an integer or it can be a float. And I also like to just demonstrate that you can do that. You can have variants that are also like tuple-like, or you can have field names. Again, roughly the same when you compile it, but when you write it, kind of fields tend to be useful when thinking about stuff. And then you create them kind of the same way as you create the struct, except you have to add the colon, and then give it the name of the variant that you're creating. So pretty straightforward. And now, finally, you have the match expression, which is like the bread and butter of working with enums, and also other things, where you match, which is it's like a glorified switch statement from JavaScript, whatever, where you match on some variable, and it's like, okay, if the variable is integer, do this. If the variable is a float, do this. Kind of easy. And there's also like a shorter version. If you only want to do something only if the variable is of particular variant, of a single variant, then you can do this if let number. You can read it. I hope. Okay. Questions. What statement? Yes.
Yeah. So getting back to the pattern matching.
Okay.
When you pass it ref 0 on the previous slide in the first section.
Here? No.
Last slide of the first section.
Last slide. Here.
First section, last slide.
First section, last slide.
Will you stop for questions next time?
Yeah, ref 0,
Okay.
right?
Yeah.
And we can read that last number is 0.
Yes.
So is it like why just a single ref 0? Like how it determines that it should be last number, not the first number, or somewhere in the middle?
Right. Okay. So yeah, try to repeat the question. So the question is like why there is a ref 0 explicitly a 0 and not like some other number. So what I'm doing here is like I'm matching. So you can match. When I'm matching, I define a pattern, and this pattern here, the first pattern that will be tried, let's say, is the pattern of some value that is a reference to specifically number 0. Right, so this is the first thing I'm trying, and then I will print. Okay, this is number 0. I know 0 exactly as a word, so I can write that. And then that doesn't work. Let's say it's a reference of 1, right? So then I do okay. Next pattern, it's a sum of n, and then n is not a value. It's a variable name. So then the value contained in the sum, so the value contained in the enum becomes a variable in the scope, and I can use this variable to print out the exact number that I actually got. So like if it's not 0, then it's an n, and then if it's actually not any number, like there is no like the list is empty, so I would get a none. Then it's there are no numbers to print, so there's no last number. That makes sense?
There is still one point.
Yeah. Why reference?
So, is it on?
Yeah.
I can see that we are collecting numbers from 0 to 10, right?
Yeah.
So the first number, not the last number, should be 0. Or am I wrong?
Yeah. No, this is just an example of the code. So this will always print 9, right? Like this is just a dummy example to show like some stuff on Rust. There's no logic to it because this is always going to deterministically do the same thing, just to show off the pattern matching.
Okay, thank you.
Okay. Moving on. So you're slowly getting to some stuff that's actually interesting. Error handling. Okay, so Rust has two different things. Rust has panics and has errors. There's a big distinction between those. Errors, Rust will force you to handle them in kind of the semantics of language kind of force you to do that, so there is no way around it. Panics are where your code just stops working and breaks down because some assumption that you've made has been violated. If you're coding for Substrate, your code should never panic. There are tools to check for that, but you can usually, when you read the code, you can kind of tell when they're going to panic. Usually it's a dot unwrap, but there are some other places. So we have two different types for doing errors. There is the option, which is either sum of some value or none, that's we've seen before. And there's also result, which is either okay or some error, whatever, which replaces what an exception would be. So there are no null values in Rust, unless you use unsafe Rust. Where we would use now you use an option, and then Rust kind of forces you to handle that. And there is the question mark operator, is very useful, that we use to propagate errors. So the option results, if you were to write it, that's kind of how you define it. So there's some option generic over T, where some is T and none is nothing. And then there's a result of T and some error U, which is okay or error, kind of straightforward. So I have this piece of code, which is add numbers. I get a slice of numbers, return a number, and I get the first and the second number, and I add them together. And this is horribly wrong, and why is this wrong? And does anyone can tell me why this is horribly wrong? Yes, so I don't know the length, so numbers 0 and 1 actually can not exist. There's another one. There's another thing that is also horribly wrong with this. Specifically, if you're like very paranoid about security. Anyone? Okay, I'll try to rush it. So the first things is like I'm indexing into a slice, but I don't know the length of the slice. So I can get a panic if my assumption about the length of the slice is incorrect. And the second thing is I'm adding two numbers, but they are specific size. I cannot this is not Python where the numbers grow infinitely. So A plus B can actually panic in debug mode when you compile to trying to figure out whether your stuff is correct or not. If the numbers are too large, so if the result of the addition would be larger than maximum possible number in 32 bits, then this will panic in debug mode. Or if your compiled to release mode, which is like has optimizations on, then it will do a wrapping addition, which may or may not be what you want to do. So we can introduce some error handling here. So instead of returning the number, we return an option of the number. So if there was an error, we'll just return a none. And instead of using the plain indexing, we do a get method, which if there is nothing there, so I'm indexing outside of the length, I get a none. And then I use the question mark operator to unwrap the option. And then if I have a none, the question mark operator will return, would do a return, so we'll stop the function, return none, and then I can carry on doing my code or running my code without everything breaking down horribly. And then at the end, I also can do like a checked add, where if there were supposed to be, if the numbers are too large and there would be an overflow, then I also just get none, and that's fine. Another way to do it, if I really, really, really want to return a number and I don't want to deal with like the options later on, I can do something like this, where I also use the get, but then I do unwrap or to get like kind of a default value. So if there's a length and there are two numbers, then I get those numbers. If they aren't there, then I just like get zeros for them. And then let's say if I'm adding two really large numbers and they kind of don't fit in the result wouldn't fit in the number type, then I just do saturating add, so it will cap out at the maximum value of the integer, and that's fine enough. And you can do like saturating add. There's checked add, saturating add. There's wrapping add. If you really want wrapping addition and you don't want to panic on debug mode, so things like that. With errors or result types is like kind of probably when most people like run into it is the file system, so IO and file system. So here I have like a simple function that reads a file from test.txt and returns a string or an error, which is an IO error, a specific error for the IO module. So first I create a file. I create a mutable file because I have to be able to like read from it. Actually, I probably don't need to. Anyway, doesn't matter. And then I create a string that I'm going to write into, which has to be mutable. And so when I'm opening the file, I use the question mark operator. So I need to like obtain the handle of the file, right? And if the file wasn't, I can't open the file, then early return with the error of the IO. So create a string, no errors there, and I read the contents of the file, and then if during the reading of the file there was my error, then again my function will return with that error, propagate error up with the question mark. Everything is fine. I return OK of the content. I'm good. There's a convention in Rust where most like crates and also in standard library will also expose an alias of the result type with the error type always like supplied, so you don't have to like type it all over it again. So like I can use the IO result of a string instead of result of a string and IO error, which is kind of shorter to write. Like it's basically exactly identical. Another thing might want to do is like, okay, maybe I don't want the result of the error. I want to just have an option. So you can cast a result into an option where if there is an error, that would just be none using the OK method on the result. So again, OK, question mark unwraps the option. Everything else is the same, and then I just use sum instead of OK. Questions? Okay, I have like 5 minutes left. I have like methods, traits, and lifetimes to talk about. So that's completely impossible. So I'm just gonna super quickly rush to them. Some implementing methods use the impl keyword. So here's like a quick demonstration. If you have a struct duck, use the impl duck to begin a block of implementation of the methods, and then you kind of write functions as you would, but you can also write functions that begin with a self that has to be the first parameter, and that kind of indicates that this function is actually a method that will take the self, and it's kind of similar to like how Python does it, where you also like write self at the beginning, and then you can like the duck and quack, and you can also like so associated functions colon function name or dot, which is a method, kind of works. And you can do references, you can do multiple references, or you can take the ownership of the thing you're calling a method to, which in this case will actually just, because there's nothing there, it will drop the duck. You can use generics. Let's not get into this. Okay. Let's also not get into questions. Okay, trait system. So traits are basically like a way to add functionality to types. And you can add functionality to types from outside. So you can add functionality to like standard library or external crates. Or you can add functionality from the standard library traits or other traits defined somewhere else to the types you have created. So you always have one of the other has to be created by you in your local like crate. Let's skip over this. So there are some built-in types, traits. There's default. There's from for convention from and into for conventing types between each other. There's display and debug for printing stuff out. I'm just implementing default, so this is kind of similar to impl blocks. Similar to impl blocks, but you also say, okay, what kind of trait it is, and then you have to like implement the specific shape of the interfaces of the trait. Skip over this. There's also the derive attribute, which is super useful. So for some traits, you can just like write this derive thing, and it will actually write the implementation for you. Let's not get into how that works. Okay, I'm gonna skip over this. It's kind of useful how to like write conversion from a number for like a simple enum. Pro tip: if you implement from for your own error type, and then you use the question mark operator, the question mark operator automatically converts whatever error type was there to your own error type. So that's pretty useful. Kind of similar. Okay, let's skip this. Oh yeah, okay, static dispatch, dynamic dispatch. There are different ways you can use traits. Usually, usually you probably prefer to use static dispatch, which is faster, like executes faster, but produces bigger binaries. There's dynamic dispatch, which doesn't duplicate code, but is slower on execution. It exists, look it up. Okay, now trait bounds. So you can define a trait that also requires that the type you implement this trait on also implement some other type. So I implement a DAG for a display type, and then I can actually provide a default implementation of a method here that will print out quacks with a self, and I don't have to know what the self is. I just have to know that okay, this will be able to be printed, and then I can implement this for a string slice. Without any actually body, because I can just use the default implementation, and then I can just do bob.quacks, right? Bob quack, and then it will print me the bob quacks. Kind of useful. Do we have questions? Let's say questions. Okay, super quick. Okay, 2 minutes of on lifetimes. So lifetimes are the bane of newcomers, and there is no analog of lifetimes in any other mainstream language. So this is basically very Rust specific. This is also the main source of like the fighting the borrow checker, which is like the phase everyone goes through when they learn Rust. But once you kind of figure out how lifetimes work, you can actually write Rust code. You can write Rust code avoiding lifetimes completely, and it's fine. But if you figure out how this works and you like really internalize it, then you'll be able to write Rust code that analog like C code would be basically magic, and you can write Rust code using lifetimes in which you're completely confident that you actually have no like errors in it. Like this is going to be correct. This is going to work. I don't, if you're really brave, like you can like even skip unit tests. You don't do that. So all references, or borrows as we call them, using the ampersand, they all have a lifetime, all of them, every single one of them. By default, that lifetime is just anonymous. And you might see that somewhere in like errors from the compiler occasionally. So Rust compiler is usually good enough to figure out, what happens when you have anonymous lifetimes. And also, examples in code usually show lifetimes as so lifetime names always begins with apostrophe and then some identifier. And examples often show just A, B, C. If you have more than one lifetime, naming things A and B and C is probably horrible, so don't do that. Like you can use names that are human readable and easier to think about. So for a simple example, I have like my DAG from previous examples. So I borrow self and I return a borrow of a string slice. So I borrow name from self. So I borrow self and I return a borrowed value. And Rust is actually smart enough to figure out, okay, I take something borrowed and I return something borrowed. It's the same lifetime. It will like live. The borrowed value has to live for like, cannot outlive of the DAG itself. And this is kind of like the way to write it. If you want to be explicit about it, you introduce a lifetime A, you borrow self with lifetime A, you return a string slice with lifetime A, same lifetime. You can do it like a bit more robustly, where you have a long and a short lifetime, and the long lifetime has to exist longer than the short lifetime. And then you can borrow self with a long lifetime and return the name with a short lifetime. And the Rust compiler will guarantee that the short lifetime lives shorter than the long lifetime, and if it doesn't, then it doesn't compile. It's kind of super abstract, no way to explain it. There's also like the static lifetime, which is the longest possible lifetime, is lifetime of the program, basically. So if you do string slices, they are all static, so they all live in the memory program. So that's kind of a tip. And just a few closing remarks. Why doesn't the stupid compiler let me do the thing? That's kind of like what you will run around and do when you do Rust. And when you're trying to fight the borrow check, you have to realize you can't win. This is a battle you cannot win. The compiler is right, and it's smarter than you. Yes, it's really smarter than you, because you're one person. The compiler is, dozens of programmers put their wisdom into it. So it is smarter than you are. But it is your friend. It's your good friend, and it's a very honest friend. It might be Dutch, and eventually, when you write Rust, you will writing the Rust code that satisfies the compiler kind of becomes second nature. And when you get to that point, you will become a better programmer, whether you do Rust or not. So that's it.
All right, do we have any questions? We have time for one or two.
Could you briefly go a little bit on how to manage private state for let's say a struct or a module? How does the privacy work, private variables?
Oh, private stuff. So I didn't do that. Basically, everything is private by default, which is the only sane default that you can have. Or say, let's go back to struct. Well, okay, let's say here, I have full of usize. The usize is going to be private, so you can see it within the same module. If you were to try to do a full .0 outside of the module, won't compile because it's private. So the way you solve that, you just put pub as a keyword before the usize type, and that's how you make it public. And the same goes for names and field names and struct themselves and basically everything else and functions. You make everything public with the pub keyword. Anything else?
Let's do a final question.
I saw a bunch of macroses in Substrate template. Yeah. And as you said, macroses are kind of magic.
Yeah.
And it's hard to figure out what they are doing if you are a newbie. And
yeah.
The question is...
I'll go further. It's hard to figure out what they do, whether you're a newbie or not. You can be a master of Rust, you still might not know what the macro is doing because it can really break all the rules about syntax. So the only way to know is if you see something, ! Go to documentation of that something, and that will tell you how to use it. I cannot tell you how to use it.
Yeah, the question, is it possible to write Substrate code without macroses? Really?
Probably.
Possible, but not advisable.
Yes. It will be very painful. But ultimately, macros unwrap to more elaborate Rust code, so we can just write that more elaborate Rust code by hand. If you're, I don't know, masochistic or something, but don't do that. Macros are there to help you. They're magic, but they help you to do things. All right.
All right, thank you very much.